Hello dear students, we are back once again with electrophilic substitution reaction. In the previous episodes you have come across the nitration reaction of benzene, sulfonation reaction of benzene. Today we will deal with halogenation reaction of benzene. Halogenation, it can be carried out with chlorine as well as bromine. If you carry out benzene reaction with chlorine, we will name it as chlorination reaction of benzene. If you carry out with bromine, we will name it as bromination reaction of benzene. We'll start with the chlorination reaction over here. So I'll write benzene first, having its molecular formula C6H6. And obviously, as we are performing the chlorination reaction of benzene, we will introduce the reaction with Cl2, chlorine molecule. The fact regarding chlorine molecule which you all are aware in your with respect to your lower standards is that chlorine is an electronegative element. The seventh group element having valence electrons 7. It is just below fluorine in the periodic table. That means it is electronegative. It has tendency to gain electron from other atom. So here the point of understanding the reaction is little bit important. We are undergoing electrophilic substitution reaction, right? And in the previous episodes we have been very much clear that we always require an electrophile to react on this benzene nucleus, and you all know very well now that electrophile is an electron withdrawing group. That means it itself is lacking electron. That means it has got a plus charge on itself. Whatever studies you have performed till date, there you know that chlorine is electronegative, so it always has a tendency to gain electrons, so it can never have a plus sign on it. You at least haven't seen that. That is the tricky part. That is the part which is important, and that is what we have to discuss in the reaction over here. But anyhow, we have to get this chlorine into an electrophile, but on its own it won't. So we need some typical, specific, precise catalyst or a reagent which will prompt this molecule to break in such a way that one atom and the other atom splits apart, but not in the form of atoms, but in the form of ions. Fine. In the form of ions, that's not enough. One ion has to be positively charged, other ion has to be negatively charged. Only then and then you can generate an electrophile. Because if one ion is negatively charged, automatically the other is understood that it has lost its electron to this one. And only then and then it will attain a plus sign, not otherwise. Fine. So here we will take a precise reagent in the form of catalyst, and that is ferric chloride, FeCl3. How this ferric chloride plays an important role, that is very important. That is the key to understand this particular episode. Fine, just concentrate. This Fe has atomic number 26, and of its number of electrons, their 3 valence electrons are shared with 3 chlorine atoms. And you know very well each chlorine has got 7 valence electrons. I am showing all the 7 valence electrons for each chlorine atom, as you can see over here. So the valence electron of Fe is shared with the valence electron of chlorine, making every chlorine atom completing its octet. There you can see. But what about Fe? You can see over here Fe has not yet completed its octet. After sharing its 3 electrons, right now it has got total shared number of electrons as 6. So it still has a tendency to attain 8 electrons if it gets a chance, right? Now what happens? The scenario, the important part starts here. This chlorine molecule we discussed earlier in this episode has to create a positive charge out of it. Okay. So what happens? A chlorine Cl2 chlorine molecule, out of it a chlorine Cl ion with minus charge comes over here. How? Let's understand first the simplest part. This is the chlorine molecule. I am splitting into 2 chlorine atoms right now because each chlorine has got 7 valence electrons. Fine. The electron is shared among the 2 chlorine atoms, where you can see both the chlorine atoms have shared their electron and completed their respective octet, which has resulted into chlorine molecule. Now, this Fe, which is lacking octet, is prompting one of the 2 chlorine atoms to form a bond with it. See, that is important, to form a bond with it. So what happens? Fe is having no electron for bond formation. So still it needs chlorine. So obviously this time the chlorine which is getting onto Fe to form a bond has to come with 8 electrons so that the octet is completed automatically, because ion is already not having its electron. Whatever valence it had, it has already shared with the 3 chlorine atoms which are existing. So one chlorine of the 2 comes with Fe. I'll highlight this one. And you can see there are now 1, 2, 3, 4, 5, 6, 7 and 8 electrons. The chlorine with 8 electrons get onto Fe. As it takes away an electron of the neighboring chlorine atom, it itself has got 1 minus charge now, because 1 electron of neighboring chlorine atom is added into it. So what happens of FeCl3? Now you have FeCl4, because 1 chlorine has got added. 1 second, it has come along with 1 more minus charge. So it is now no more FeCl3, but it has converted into FeCl4 minus. On the other hand, the bonded chlorine has lost its electron to its neighboring chlorine atom or bonded chlorine atom. And so this chlorine is now, you can see, having 1, 2, 3, 4, 5 and 6 electrons. Earlier it had 7, where it had shared 1 electron. That's taken away by this chlorine atom, and so it has got only 6 valence electrons. So now this Cl is lacking electron, and that I am showing with over here with a plus sign, you can see. So our criteria of the title electrophilic substitution reaction has been fulfilled over here. We have received a chloronium ion, which is nothing but it is your electrophile. So the overall mechanism has taken place this way. Now this chloronium ion, rest things remain the same as we had discussed in earlier episodes of nitration and sulfonation. This chloronium ion gets attracted towards the benzene nucleus. There is a pi electron cloud above and below the plane of benzene. So that prompts this chloronium ion to get attracted. So this Cl with its plus charge gets attracted on the benzene. A carbon bonded to hydrogen, right? Hydrogen leaves the carbon, leaving its electron, finding this chloronium ion getting onto the benzene nucleus. As a result, what happens? The carbon from which the hydrogen leaves, that carbon becomes electron rich. The chloronium ion attacks the same carbon with its plus sign, and as a result, the plus N minus of each atom gets nullified to form a bond, and as a result finally we form the compound named as chlorobenzene. Got it very clearly? Fine. Okay. What is next? The H which left the benzene nucleus, which left the carbon, has now got plus sign because it leaves its electron behind. That is your proton. That H plus combines with FeCl4 minus, and that H plus takes away one Cl minus which was introduced in FeCl3 and forms a byproduct HCl, hydrochloric acid, HCl. Thus HCl is formed as a byproduct. Product is chlorobenzene, and the most important thing, ferric chloride is obtained once the reaction is over. So I would say that over here ferric chloride is your catalyst. The overall reaction occurs in presence of sunlight, or you can even heat it. So we can write over here heat or sunlight, H nu. So this is the condition. The same chlorobenzene can undergo further chlorination with the same catalyst FeCl3, and that can give you further product. So this is the overall mechanism of single chlorination reaction of benzene. Same way you can proceed with the bromination reaction. Same scenario, everything remains the same. The further chlorination reaction of chlorobenzene will take in the next episode, and there you can again understand the same phenomena. I think now this mechanism must be very clear to you people, and so we will continue with the next part once you are getting thorough with this part. Fine. So wish you all the very best. Prepare it thoroughly and then join with me for the next episode. Right? Till then, prepare well. See you.